So, okay, so I'll start then. Yeah. So, okay. So, bit of a background. So, this is basically my final year project, and we completed it December itself. The title is basically a client-side search using spectral bloom filters. I'll explain what client-side search is, and then I'll explain what spectral bloom filters are and how we are integrating that, right? So this is what a traditional server-side search looks like, right? You be a client, basically, let's say your computer, it sends a request for a homepage to the server. Let's say it sends a request to Google, and the Google basically sends its homepage back to the client, right? And then you see your the search tab and you type your query there, right? And then you press enter. So it takes the search query to the server, and then the search responses are written back to the client, right? So this is what a traditional server-side searching looks like. It's been there for decades, and it works really well. Now, what is client-side search? So client-side search is basically you request for a homepage, let's say some XYZ homepage, which is a search engine, some search engine or something. It gives you back a response. And now you don't need to request anything else to the server. So whenever you're searching for a search query, the entire processing part, the entire ranking part, everything will be done at the client side itself, here at the client side. You don't need to send any request to the server again. And the search responses will be generated at the client side. So this is what client side searching looks like. Now, where does this client side searching, like where is it really helpful? So like it is usually very helpful for static websites, so websites where there's not a lot of dynamic content involved, maybe documentation, blogs, online portfolios. So it is really useful for such static websites. It just like you don't need like a full blown search functionality like Google custom search, which many blogs use. You don't need that. Client side search works very well. How is client side search being performed today? So there's a very famous library called Lunar.js, which employs this technique, client side searching. Now the issue with Lunar.js is that it uses something called an inverted index, right? So what inverted index is basically something like you just imagine it to be like a Python dictionary. It's not exactly, but something like that. There's a key is your particular string. So let's say if this is your entire document, this entire slide is your document, then there would be a key called how, and then the value will be the location, which is the slide 6, right? So look, it will show you slide 6. This entire thing in terms of link. So that is what inverter index is basically. There's a value, like token value, and then there are places where that token was actually found, links where that token was found. And so using that entire thing, like monstrous, and the entire thing is basically stored in some kind of JSON files or something like that, which inverter index does. And then it is sent to the client on the first request itself, and it stays there. It is basically, there's a dynamic like JS script involved, where if a person basically clicks on the search box, then at that point it sends the request, the JSON file, the inverter index, to the client side, and then the entire searching happens in the client side. Now what the issue is that the size, it is really big. Like in some cases it goes to like 5-10 megabytes or something like that. The size here is proportional to the size of the entire blog or the portfolio or something like that, right? So this, like if your scope is really big, then this just doesn't work, right? So it is not scalable, right? So it steals on an extreme end of the spectrum. And so there is the entire memory accuracy trade-off involved here. Now it gives you, inverted index method basically gives you 100% accuracy, because all the tokens are stored and all the links corresponding to the tokens are stored here in the client side, right? So 100% accuracy in that regard. The searching is really efficient, but the size is not that great, because as I said, it is storing every single detail there on the client side. So it can really blow. In fact, I'll show you the data which we have gathered. It's monstrous. uh, so that is what invert index is about. And it can consume a larger bandwidth, right? I mean, it's obvious you don't want that to happen. You want your websites to be lean, right? And even the user experience is affected, right? So a new idea came into picture. Now, this idea was somewhere in 2013, I think. I'll actually show you the blog. So there's a reference. Okay, so this is the guy, S. Korokitakis, and he basically wrote a blog post about this, where you can basically write a search engine using Bloom filters in 2013. But the idea was like, even like, okay, so I'll basically explain you what Bloom filter is a bit later. But the idea with Bloom filters was that it dealt on the opposite end of the spectrum. So uh, while the inverter index method, it was just dealing with the efficiency, right? The entire efficiency thing, and not about the size, right? Inverted the Bloom filter method, what it does is it deals entirely on the size scenario and not much on the searching. So if you use basic Bloom filters, in this case they are using tiny search is using Cuckoo filters, which is again a library which does client side searching. But if you use like basic Bloom filters, you're going to get random results, like completely random results. There won't be any kind of searching involved, and I'll explain you why that happens in a little bit. But the size is really efficient, like, because it is probabilistic in nature. The entire data structure Bloom filters is probabilistic. So you control your size. You tell Bloom filters, okay, I'm okay with this kind of sizes, and you can basically tune that size. I'll show you how you can tune the sizes later on. So you see the current scenario before we came into picture, the current scenario was that there were two different libraries which were dealing on the extreme ends of the spectrum. And so our goal was basically to get a middle ground here somewhere, right? And in comes Bloom filters. So no, okay, that's a bit later. Okay, I'll first explain Bloom filters. Yeah, okay. So I explain Bloom filters first. So I think, like, instead of like showing equations and stuff, I think this is a very nice website to just understand Bloom filters very quickly. Um, you can see this website, right? Yeah, okay. So so this is basically a bit array, all right? Bit array. So every position here is of, just assume as a 1 bit, and it stores two values, zeros and ones, right? Now I'm going to enter a string here. So let's say I enter a string called apple, right? And then I want to add it to this Bloom filter, right? This is a Bloom filter, right? So now so you can see there are two hash functions involved. So it took the string, it hashed it using two different hash functions. One is fnv and the other is murmur, right? And fnv gave a hash index of 2, and murmur gave a hash index of 1. So what this Bloom filter did was it took that string, and it basically hashed at location 1 and location 2. So you can see that both those locations are green. So now you might be thinking, how can we use it for searching, right? So, like, so basically searching is entirely composed of tokens, right? So what you can do here is, let's say you want to search not many, just 3 documents. You want to search 3 documents, right? So you'll create 3 different Bloom filters: Bloom filter 1, Bloom filter 2, Bloom filter 3. You take the Bloom filter 1, matching it to document 1, right? All the tokens in document 1, you basically hash it many times. Like, maybe you want to hash it 2 times, 3 times. I'll show you the optimal parameter later on, but you hash it some x times, something like that. And you basically uh, put that location inside the Bloom filter. Now, how can you search it? So now you can basically test an element is in the Bloom filter or not. So if I search apple right now, so it shows, is the element in the set? Maybe. Why? Because those two, when it searches, it again hashes that value at the client side, right? And it gets the same two tokens, 2 and 1, right? And then it goes up and it sees, okay, is there a check at 2? Is there 1 at 2? Right? Is there a 1 at 1 position? Yes. So this can be inside the Bloom filter, right? Now, if I search something else, like, I don't know, game or something, so game does not give you that, right? It shows you 9 and 9, right? So is the element in set? No. So you can basically understand whether an element is there in a set in Bloom filter or not, just by this very simple membership function, right? And this is very interesting because you don't need to store data at all here. You just need to, like, hash it, store the indexes inside a Bloom filter, and your job is done, right? Now, what is the issue with this Bloom filter? Before I go with the issue, I'll just tell you how to tune the optimal parameters. So there are three parameters at play here, right? There is K, there is M, and there is E, right? What is K? K is the number of hash functions you can use. So in this case, we are using two, right? But here we want to optimize K, right? So K is a parameter to be optimized, right? What is M? Now M is basically the length of the bit array. So in this case, I think it was 15, right? 15, 0 to 14, right? So that is again a parameter which we want to optimize, right? But now there are two parameters which are at play and which we as users control. First is the error value E, and the second is the number of tokens, right? So when you have a document and the document has 100 tokens, as I said, document corresponding to a Bloom filter, so you already know that n value, and that n value is always going to be fixed, 100,000. It depends on the number of tokens there in a document, right? Number of elements there in the document, number of words there in a document, right? But E, what is E? So E is basically false positive error. Now Bloom filters, they generate false positives, right? They are probabilistic in nature, and there is a chance that they can have false positives. A very quick recap about what false positive is. So if a model is predicting something to be yes, and in reality it was a no, then we that is an incorrect prediction, and it is called a false positive, right? Again, for false negative, if a model is predicting something as no and in reality it was a yes, then it is a false negative, right? So in case of Bloom filters, it generates false positives. So there are chances where Bloom filters can say something like yes, some you can see here, observe here that even when I type apple, it says maybe, not yes, because it can never be 100% sure. There can be a chance that I enter some other value. Let's say I'll just enter orange and let's see. Okay, so orange got indexed at 8 and 13, right? Something else, pine. Uh, Pine got indexed at 6 and 10. Okay, so I'll just go on and see Parth. Parth got indexed at 3 and 9. Okay, so all are unique right now. This is very interesting. And just man, and it got indexed at, there's a collision. See, it got indexed at 1 again and 13, right? 13 is new, but I believe one was already indexed by Apple, right? If I search Apple again. So you can see uh, now false positives are being generated, right? So there is a chance that such false positives can be there. And like, so this is basically the intrinsic property of very simple Bloom filters, right? So now how, like, the issue with this Bloom filter is it is really space efficient. As I said before that tiny search was using Bloom filter variant Kaku filters, and it is efficient to some extent. But the issue back then was that there was no ranking involved, right? If you use traditional Bloom filters, if you go by the blog post he wrote in 2013, there's absolutely no ranking involved. So everything looks really random, right? All the results are random. There is no kind of consistency. And I mean, you just don't want to use random results, right? When you are using a search engine, right? That is the entire reason why people use Google, better search results. So how can you basically add search result functionality, right? Now, what is missing from Bloom filters? There's one thing missing from Bloom filters, and that is counting, right? Because it is storing everything as zeros and ones in one particular index, there's no counting involved, right? So how can we add counting here? Now, to add counting, we can basically use something called counters, right? And that is where counting Bloom filter comes into picture. So you can see this is a tradition. Oh, can you see this slide, right? You can see, okay. So this is the traditional Bloom filter, right? There's ones and zeros. But on the right hand side, you will see that this is counting Bloom filters. So what are counting Bloom filters? Basically, what you do is uh, you divide this entire thing into counters, right? So if this is a 15 thing, let's say I'll divide it into counter size of 3, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 9, 10, 11, and so on and so forth. So what this 0, 1, 2 will do is it will store one value, not three different values, just one value. Now, because there are three positions involved here, so it can store a maximum of like 1, 1, 1, right? Which is, in this case, it is 7, right? So it goes from 0 to 8, right? So 2 raised to 3, 2 raised to n values it can store, right? So that is where counting, you can basically, by combining those bits, right, and creating those chunks counters, you can basically add counting. And when you add counting, you add search, right? Because in search, what we want to do is we basically want to know how many times a particular token entered, right? Like how many times a particular token was seen in this document, right? What was the frequency of that particular token in document? If the token's frequency was nice, good enough, then you can all perform all those nice search algorithms like TF-IDF and Okami B25 and something like that. So you need that counting values, right? So that is where counting Bloom filters comes. But we cannot stop here. Why? Because counting Bloom filters has a big disadvantage, which is called count mismatches, right? So what is count mismatch? That's that's a good question. So the second diagram figure, which you can see, it basically explains you count mismatches. So there are three tokens. There are two tokens called T1 and one token called T2 token, right? And again, you do the same procedure. You hash it, so you get 1 3 1 3 and 3 6, right? You go to 1 3, you go to first position, you increment counter. This time it's a counter to 0 1. You go to 3, you increment it again to 0 1, right? So but here's the issue with count mismatch, counting Bloom filters and count mismatches in particular. You see there is a hash collision here. Both token T1 and T2 have one index called 3, which is basically, they are basically indexing at the same position. So what is happening is there's this token called T1, it is indexing at a particular counter called 3, and it gets incremented to 1. But then another token T1 T2 comes into picture and it increments it to 2. And the first one thinks that, oh, my count was 1, but the second value thinks that second value does not even know. Both have a value of 1, but in reality it shows as 2. Why? Because two tokens, they indexed it at the same counter, right? So there's a mismatch taking place. So count mismatches is basically something like, if I have to just define it in one sentence, then a frequency of a particular word inserted in a counting Bloom filter, if it differs from its actual frequency in the document, right, then we say a count mismatch has occurred. So in the actual document, it says something like frequency is 3, but because of this entire increment again, it shows 5, then that is a mismatch, right? And it can affect your results and can inflate your ranking and everything. So counting Bloom filters is not optimal. So we cannot stop here. So what to do next, right? So this is where the title of a paper, Spectral Bloom filters, comes into picture, right? What Spectral Bloom filters does it original Spectral Bloom filters paper introduces three operations called minimum selection, minimal increase, and recurring minimum, right? We are not going to deal with recurring minimum in today's show and tell because it's not relevant to this topic, right? So I'll deal with minimum selection and minimal increase. So what is minimum selection and minimal increase? Now, minimum selection, what it says is, uh, so like even in this case, yeah. So what it says is, okay, so there are two values, 3 and 6, right? And 3 is currently, there's a mismatch occurring and it is 3 value. But at 6 position, it is still 1. So what minimum selection says is, you hash it multiple times, like let's say k times, as we saw, let's say 3 4 times, right? And you get those 4 different values. Now you choose the value which is the lowest, which is the minimum, because that assures that there is least amount of count mismatches occurred, and there's always a bound involved here. Like you can get that assurity. So okay, so if you choose the least amount, it is closest to the estimated value as compared to the maximum amount, right? So that is minimum selection algorithm. And minimal increase would be, now using minimum selection, only minimum selection won't work, because even if you just select the during querying processes, if you just select the minimal value, it can still inflate your rankings, and it can still um, give you error, like not great search results, right? So then they introduce a second algorithm called minimal increase algorithm. Now what it says is that in this case, you can see that it was first token T1 was indexed at 1 and 3, right? So one position got 0 1, right? First it got incremented to 1, and third position got incremented to 1 again. But then a new token came in T2, which we know that it was it basically had a collision, right? There is a hash collision involved with token with the third index, right? So we don't increment the third value again to 2. We leave it as 1, right? And we check the sixth value. Is it below 1? If it is below 1, then we just increment it. So the idea behind minimal increase is that you only increment the minimal values. That's it. You don't increment, and you find out, you take a pass, you only increment the minimal values in your hash. You don't even need to take a pass, because you just have this k hash function, the concrete indexes. You can just do a that direct search, right? If you're using, it depends on the data structure. Usually this is done in bit array, so you can direct indexing is done. So that way you can actually prevent uh, during the insertion time itself, you can prevent count mismatches, right? And then when you do minimal selection, it again gets reduced, the entire uh, count mismatch gets reduced. So I'll show you a very quick example. In case this is still a bit blurry, I'll show you a very quick example regarding this, which I prepared. So example of minimal selection, minimal increase. So this is a document, very small document. The document name is apples are apples, lemons are apples. Right? This is the document. And so this document has 6 tokens, right? Apples are apples, lemons are apples. So there are 3. Apples has a frequency of 3, R has a frequency of 2, and lemons has a frequency of 1, right? So we start with 2 tokens at a time, right? Very simple, 2 tokens. We are using murmur hash here, right? There are even the seed values I mentioned. This is the actual example which I've performed, and then I've converted it. So we increment the first 2 tokens, which is apples and R. So we hash apples first, right? We get the locations 9 and 2. So we go to 9, right? We increment it to 1. We go to 2, we increment it to 1. Then we take the word R, we again hash it, we get 3 and 8. So we go to 3, we increment it to 1. We go to 8, we increment it to 1. So this is how it looks like: 1, 1, 1, 1, right? After the first step, we take the next 2 tokens, apples and lemons. Now in this case, apples and next 2 tokens, you can see that apples when hashed goes to 9 and 2. Very simple, no hash collision involved, right? So we go to index 9, we change this 0, 1 to 1, 0, right? 2. And we go to 2 again, and we change 0, 1 to 1, 0 again, right? 2. Now lemons, this is where interesting part again. Okay, so lemons has a hash collision, right? It There's a hash collision at 2, right? So when it hash, goes to it, basically gives you indexes 2 and 10, right? So now here's where minimal increase comes into picture. We are not going to increment. We'll check. Okay, we'll go to 2. Okay, so 2 has a value of 0, 1. We go to 10. 10 has a value of 0, 0. So 10 is lower than 2, right? So we'll just increment the minimal value, which is 10th index, and we'll leave second index as it is. So what happened here after this step was that 9 and 2 got incremented to 1010, but 10 remained at 01, right? And the benefit of doing that was that when you are going to query in the future about lemons, right, it is going to check the second place and the 10th place, and then it will use the minimum selection algorithm, and it will select the lowest value, which is the 10th index, and the value will be 1. So the number of tokens will be 1 and not 2. So right, so that is how it prevented that count mismatch, right? So you can see now the entire thing is starting to come into picture. And the last 2 tokens, apples and R, again there's no hash collision between them, so they again go to 3. This thing gets incremented to 3, 3, and because the R gets incremented to 2, right? So done. Now you can query, and as I said, when you query for lemons, you get 1 and not 2, right? So this is how spectral bloom filters work. There's another algorithm, as I said, recurring minimum, which is used for deletion operation. So if you want to delete something from a bloom filter, then how can you do that? Now the reason we're not using that is because no one wants to deletions. I mean, basically you're just taking the tokens, and then you're creating a bloom filters, and then you're just storing the tokens at the client side, right? There's no deletion part involved. You don't want to delete anything. And even if you want to like change block, like things, you probably want to remove 2 blocks or something, you can always generate a new entire architecture at the client side again. So you don't need that deletion operation. It just waste. So we never used it. But you can explore this further. The entire thing was created by Yossi Matias and Sar Cohen, Spectral Bloom Filters. It's a bit old, I think 2003. Yeah. So this is what spectral bloom filters is. I've already explained this. I'll just skip this. Okay, so this is interesting. So this is how our system architecture looks like, right? I'll just, yeah. So this is how our system architecture looks like. There is documents. You take the documents, as I said, right? There's a block, right? Block has different documents, doc one, doc two, different blocks, different documents, right? You take the text from that document, you perform pre-processing on the document. So what is pre-processing? Like any pre-processing operations now, basically you just um, like you remove the basically you want to, because these documents will usually be in HTML, so you want to pass the HTML for the content, right? So you will remove the header file, the tags and everything, and then you'll convert them to lowercase. You'll remove all the punctuation, filter all those stop words out because they don't help in searching and stuff. And so all the pre-processing is done. Now interestingly, we are not doing sophisticated pre-processing techniques like lemmatization or stemming. Now the reason we are not doing that is because we don't want to overburden the client side too, right? Because whatever we have to understand, whatever we do at server side while generating this spectral bloom filters, we'll have to do exactly the similar pre-processing at the client side stage itself, right? And we don't want to do that because it just increases the size and the complexity at the client side, does not help a lot. So we are not doing any kind of we are not doing using any kind of lemmatization or stemming here. So we have done the pre-processing, right? And we got the n tokens, as I said, n number of tokens, and then this is the error value e. Now usually you can pick an error value of 0.01 or 0.1. 0.1 would be basically 10% false positive error, and 0.01 would be like 1% false positive error, right? So you can just tune that false positive error, and as you tune that false positive error, the size of the your bloom filter, spectral bloom filter, and the number of hashes required would change accordingly, right? So for a very small, it will change, like, and for a very large, it will probably be a bit low. The size would be a bit low. So if you want, like if you have an error of 0.1, the size of your spectral bloom filter will be small as compared to if you have a error rate of 0.01. Why? Because it basically needs, the entire play is about reducing false positive, right? And the only way you can reduce false positive is by increasing the length and storing that much information inside the spectral bloom filter in the hope of reducing false positives, right? So you just generate the bit array after that, and then we do the indexing and encoding stuff, which is actually required. I'll show you that indexing and encoding in our paper. And after the indexing and encoding, you this kind of spectral bloom filters are generated as .bin files, binary files. I'll show you a demo of that again. And then you just take the binary files and you basically encode it into a client side document, which is basically just an HTML page, right? By default, our library creates it as search.html, and it gives you a very standard UI as well to search things, right? So the entire client side document is created. You take those spectral bloom filters, you do the encoding on that spectral bloom filters, and you generate your client side document. Now when a user searches for a word, you take that word, you pre-process it, the same pre-processing you did at server side, you generate all the tokens, and then you basically do the ranking and everything done at client side here, and then you send all those ranked documents back to your user, right? Document your website, right? So I think I've explained this pre-processing step and bit arrays. Yes, encoding and decoding. So how we are doing those encoding and decoding steps. So I'll show you that. So, mhm. So this is like, so this is one of the, you can see here, this is an example of encoding technique. So what we basically, how we do it is that you take this entire bit spectral bloom filter, right? It solves the ones and zeros. We have not divided into chunks here, just so that it is easier to visualize and stuff. And what we do is that we basically divide this entire spectral bloom filters into 15-bit chunks, right? So we divide it into 15 big chunks. So it is size is 20, right? So yeah, so we divide into 15-bit chunks. Now the first 15-bit chunks can be done easily, 0 to 14, but the next you cannot do it because there are just like 6, right? and you need padding here. So we just padded with zeros in the end. So you can see this padding with zeros in the end. And so you get two chunks. In this case, you get two chunks of 15 and 15, right? And then we basically, because we have padded a particular value, in this case, we have padded what I think 6 or something, nine. We have padded 9. So we have to like, what we do is we just mention that padding thing in the start of the entire encoded string, that this is the number of things we have padded, and then we just basically convert this entire thing into some our algorithm called base to p15, right? And we just generate the unicode values for that, right, after adding an offset, and we basically merge everything together into the encoded string. So eh, what we are sending it um, what we are sending at the client side, the document search document we're sending it client side, basically contains an encoded string which has searching for a particular document. And in this case, you can see it is 9 and then some unicode values, right? 9 is basically 9 padded, right? So we found out that, so this is basically it is, the formal name is base 32768, which is I believe 2 raised to 15 encoding technique. We found that this was really optimal for our use case as compared to other encoding techniques, and it produced like 93.75% efficiency, which is basically the ratio of the input bits to the output bits. Input bits being this entire yeah, spectral Bloom filter bits, and output bits would be the ones generated here, right? So and again, you don't even need to, the interesting thing about this encoding technique is that you don't even need to like decode it at the client side. You can just index places here and directly do stuff. So it is really convenient, the encoding decoding technique. um, and processing queries at client side. So what kind of ranking is currently, so what kind of ranking can you use at client side, right? All kinds. In most of the cases you can do all kinds of ranking. Second, yeah, okay. So this is actually a paper and which we published, and so this is a very simple term frequency ranking which you can do. But the issue with term frequency is that you can get very skewed search results. You can perform TF-IDF ranking, which is what is currently shipped when you are using our library, right? It is shipped by default, TF-IDF. This is the TF-IDF formula, right? And you can even perform Okapi BM25 ranking and all the sophisticated ranking techniques. They are all supported by the library, and you can perform those as well. So so even ranking works. So finally ranking works here in this case, right? As I said, um, this was what was missing from both those libraries, right? So I'll basically show you the results here. So we tested our entire thing on 4 different blogs, right? Danlu, Endler, my blog, and Matthew Daly. And we also tested our results on a very large data set called a 4,000 short stories data set. It had a size of 80.3 megabytes, and it contained 4,071 short stories. So a lot of short stories, yeah. And this basically done to just to see how does our model behave on very large data sets, right? And we found some really interesting results. So this is this is the performance section, right? So we use the list of like 20,000 English words to query the spectral Bloom filters, and we basically checked whether the estimated error frequency was matching with the actual error frequency E, which was basically given by the user. And we found out that it was really close. Like for 0.1, we were basically getting somewhere around 0.05 to 0.7. And for like 0.01, we were getting somewhere around 0 to 0.02. So it was in accordance with what we hoped, and in accordance with what the actual error value which the user was sending, right? And in count mismatches, as I said, so like how is it performing against count mismatches? So for like when your error positive is 0.1, the count mismatches are very low, something around 2 to 11. And when it is 0.01, it is somewhere around 0 and 1. So there's like, if you're using 0.01, you don't 0.01 false positive error rate, you don't need to worry about count mismatches at all. You won't be facing that issue, right? And this is the our model on larger data set, the 4,000 short series data set. And you can see that the results are almost similar to the smaller blocks, right? So nothing has changed in that regard, and that is interesting because it shows that our model is scalable to even larger data sets, something larger document sizes, right? Something which Lunar.js was not able to do. I'll show you that. So this is by far the most interesting result section. It is about size comparison. And on table 5 on the right, like bottom right side, you can see that Luna generates an uncompressed size of 349 megabytes using the inverted index method. And by comparison, if you use spectral bloom filters with 0.01 false positive error rate, it generates 43.6 megabytes, right? There is an 8 times difference between like the most promising model currently in market and our model. And if you use zero point 0.1 false positive error rate, it goes even, it halves itself and goes to 21.7 megabytes. So we have like finally balanced that thing, which I said that both the libraries, Luna.js and TinySearch, they were dealing on extreme ends of spectrum, and ours is somewhere between. So it is performing really good on size comparison. And this is the search result comparison, and I'll show you how it performs well on that as well. So on the left hand side, you can see that it is being Lunar and Lunar.js and our models is being compared, and you can see that. So we have basically used two metrics called Kendall-Stowe and Spearman foot rule. I'm not going to go in detail about that because it's not really important. But what I'll say is that for a perfect correlation, that is, so when you're comparing search results, you want a perfect correlation, right? So what is a perfect correlation? If if Lunar is generating a particular ranking, and if spectral bloom filter is able to perform like generated very similar ranking to the one generated by Luna, then that means that there's a high correlation between those two rankings, right? And that is very important because Lunar is, by as I said, it has the best ranking involved, right? It stores everything in the client side. The entire inverted index is being stored at the client side. So we are expecting it to have like the most efficient client side searching, right? So how does a model perform against that, the best searching? So you can see that for like, if you can see this part, the Kendall Stowe, in many cases, like we observe that we basically search for particular words. We cannot search for entire words because we were basically dealing with like 3-4 languages. One was in entirely in JavaScript, other was in entirely in Rust and Python. Our model was in Python, so it was really difficult to like create an automated process to do all those, to calculate for all the words. So we chose the high frequency words and we perform search result comparison on those words. And we found out like in this case, you can see that there are many words who have a correlation greater than zero point 0.5, right? But on the right hand side, you can see, which is comparing itself with TinySearch, that many values are in negative, many are zero, some don't even have any ranking involved because there's just one document in common, right? And even though a document which has a perfect correlation, it just has two documents in common out of 10 documents, right? We were searching for 10 documents, like that there was a limit. So you can see it performs really bad. As I said, it was completely random, so there's even no even searching. So you can see that like we basically as Luna and TinySearch, they dealt on the extreme spectrums. What we produced was something which was able to balance the memory and the search efficiency trade-off, right? So that is the interesting part. I'll quickly show you a very small demo. Yeah. Um, right. So you can see that our library is called Sthir, which in Hindi means static, right? Because we are doing static searching. So I did an ls here just to show you there are HTML documents there. And now it is going to just, because we have put it on pip, so you can basically do Python 3.6 minus m dash m pip install still, right? And still gets installed. And I'll quickly again do the ls thing. You can see, just to show you that there are documents here. HD. Oh yes, you can basically use stir edge to get a help functionality here. So Yeah, all the arguments. You can change the counter size, you can change the error rate, as we said. You can even add a limitization thing, but I think that is still in works. So you can see there are 5 documents here, 5 HTML documents, right? And it basically gives an error rate of 0.01 with a counter size width of 4, which is like 2 to 4. So 16, it can count up till 16. The counter size is 16. So you can see these are the binary files which have been generated for each document, right? And then you can see when you do an ls here, you can see that there is a search.html page which is automatically being generated by the library for you. And all you need to now do is just open a Firefox browser, like your favorite browser, and you can just search for the particular word, right? And all the instance will now, like all the ranked results will now be shown on the client side, right? So yeah, it showed all the ranked results on the client side. So you can actually check this library out. It's there on GitHub. um, I'll share that link with you guys. Um, yeah, I think that's it. Yeah.